Hey guys, welcome to another video in my AP Biology or Biology Olympiad prep playlist. In the last video we discussed the structure of an atom, and in this video we're going to be talking about different chemical bonds that can be formed between atoms. So let's get started. Chemical bonds are basically just interactions between atoms' valence electrons. All atoms want is to be stable, and the only way they can achieve this is to have a full valence shell. So atoms with partially filled valence shells form chemical bonds to gain or lose electrons and become stable. Now there are 4 types of chemical bonds that you need to know. Covalent bonds, ionic bonds, hydrogen bonds, and Waals interactions. In covalent bonds, the 2 atoms bonding share their electrons. Let's take a look at a water molecule, for example. A water molecule, or H2O, has 1 oxygen atom covalently bonded to 2 hydrogen atoms. A hydrogen atom has 1 valence electron, as shown in that diagram, and an oxygen atom has 6 valence electrons. In order to have a full valence shell, a hydrogen atom needs to gain 1 valence electron, and the oxygen atom needs to gain 2 valence electrons. Let me draw the Lewis structures to make this simpler. For hydrogen, you have the H with 1 dot indicating its 1 valence electron, and for oxygen you have the O with 6 dots for 6 valence electrons. Now let's take a look at how this bonds. Again, we've got the Lewis structure for oxygen and 2 hydrogen atoms. The bonds form over there and there. So essentially, what's happening is you have an oxygen atom in the center and 2 hydrogen atoms bonding like this. Oxygen has 4 valence electrons that are not shared, and it shares 1 valence electron each with each hydrogen atom. And the hydrogen atoms share their 1 valence electron with the oxygen atom. So as you can see here, what ends up happening is the oxygen atom has 8 valence electrons, meaning it has a full valence shell. And each of the hydrogen atoms have 2 valence electrons, meaning they also have a full valence shell. And they're all stable. So by forming this compound and covalently bonding, all of the atoms are stable and have a full valence shell, and they're happy. But covalent bonds don't necessarily have to be single bonds. You also have double bonds and triple bonds. Let's take a look at O2, or oxygen gas, for example. In this molecule, you've got 2 oxygen atoms. Oxygen atoms have 6 valence electrons, as we saw before. Now, to have a full valence shell, each of these oxygen atoms need to gain 2 valence electrons each. So what happens is they bond to each other, and instead of sharing just 1 electron, this oxygen atom here shares both of its unpaired valence electrons, and the other oxygen atom also shares both of its unpaired electrons. So they share 2 electrons with each other to end up having a full valence shell, and this is what the molecule ends up looking like. Now let's look at triple bonds. Compounds with triple bonds, for example, you've got nitrogen gas, or N2, where you've got 1 nitrogen atom triple bonded to another nitrogen atom, or C2H2, where you've got 2 carbons triple bonded to each other and 1 hydrogen single bonded to each of those carbons. Again, here, instead of sharing 1 electron or 2 electrons, each of these atoms is sharing 3 electrons. Now, there are two types of covalent bonds that you need to know. You have polar covalent bonds and non-polar covalent bonds. In polar covalent bonds, one atom is more electronegative than the other. This means that it attracts electrons more. Attracts electrons more. So basically what this means is that the electrons spend more time near this more electronegative atom, or basically it hogs all the electrons to itself. And what this does is it gives this more electronegative atom a partial negative charge, because electrons are negatively charged and they're spending more time with this atom, and that creates a polar molecule. Now, non-polar covalent bonds, both atoms are equally electronegative, meaning the electrons are equally shared between the two atoms. For example, an example of a polar covalent bond would be hydrochloric acid, or HCl. In this, you've got one hydrogen atom covalently bonded to a chlorine atom. Chlorine is way more electronegative than hydrogen, so it pulls all the electrons towards itself, and it creates this dipole moment where chlorine has sort of a negative charge and hydrogen has sort of a positive charge. And this creates a polar molecule, like I was mentioning before. Now, for non-polar molecules, we've got, for example, methane, which is CH4. Carbon and hydrogen are equally electronegative, so electrons are equally shared between them. Now, let's look at another example of a polar covalent bond. Let's look at a water molecule. In a water molecule, we've got an oxygen covalently bonded to two hydrogens. Oxygen is way more electronegative than both hydrogens, so it hogs the electrons towards itself. Because electrons are negatively charged and they're spending more time near the oxygen gains a partial negative charge. And since the electrons are spending less time near the hydrogen atoms gain partial positive charges. Now, when this water molecule comes in contact with another water molecule, again, hydrogen atoms have partial positive charges, and oxygen atom has a partial negative charge. The partial positive and negative charges attract to each other, and this attraction forms a bond called a hydrogen bond. Now, for a hydrogen bond to occur, there are two requirements. The hydrogen has to be bonded to a fun. Fun is an abbreviation for fluorine, oxygen, or nitrogen. So the hydrogen has to be bonded to a fun, and it has to be attracted to a fun. So in the water molecule here, the hydrogen is bonded to an oxygen and attracted to an oxygen. But let's look at another example. If we've got methane, or CH4, and a water molecule, will this hydrogen and oxygen form a hydrogen bond? I encourage you to pause the video and figure it out yourself. Alright, no, this will not form a hydrogen bond. This is because the hydrogen is bonded to a carbon, and that's not a fun. And one of the requirements for a hydrogen bond is that the hydrogen has to be bonded to a fun. So there won't be a hydrogen bond. That's all you need to know about hydrogen bonds for now. But moving on to ionic bonds. In some cases, one atom is so much more electronegative than the other that instead of sharing their electrons like in a covalent bond, it steals the entire electron for itself. Now, this causes an imbalance between the number of protons and electrons in the atom. And because the number of protons and electrons aren't equal, the atoms become charged particles called ions. The atom that gains an extra electron has a negative charge and is called an anion. So it has a negative charge and it's called an anion. And the atom that lost its electron has a positive charge and is called a cation. Now these positive and negative charges are attracted to each other, and that results in the formation of an ionic bond. But let's look at an example. Sodium has one valence electron in its valence shell. And chlorine has 7 electrons in its valence shell. Chlorine is so much more electronegative than sodium. So instead of sharing their electrons, it completely steals the electron from sodium. This results in chlorine and sodium both having a full valence shell. But because chlorine gained an extra electron, it has more electrons than protons, so it gains a negative charge, which makes it the anion in this case. And sodium lost an electron, so now it has more protons than electrons, so it has a positive charge, and it is the cation in this case. Now the positive and negative charges attract and form an ionic compound called NaCl, or sodium chloride, or table salt. Ions don't necessarily have to be charged atoms. They can be charged molecules, like you've got ammonium, which is NH4+, or hydroxide, which is OH-, or sulfate, which is SO42-. Now, moving on to our last chemical bond, the weakest ones, van der Waals interactions. In any covalent bond, even the nonpolar ones, the electrons are not evenly distributed all the time. Electrons are freely moving in a given space. You can't put them on a specific path and expect them to be evenly distributed all the time. Sometimes the electrons may be concentrated in one area of the bond. For example, let's look at a methane molecule, which is one carbon covalently bonded to 4 hydrogens. In this example, let's say the electrons are concentrated near a hydrogen. This will give the hydrogen a partial negative charge, and it will give the carbon a partial positive charge. Now, when this molecule comes in contact with other molecules, whether they're polar or nonpolar, it will stick to them. In this case, let's look at a nonpolar molecule like C2H2. You've got 2 carbons triple bonded and 1 hydrogen single bonded to each of those carbons. In this case, let's say the hydrogen has a positive charge and the carbon has a negative charge. These 2 charges attract to each other because opposite charges attract, and it causes these molecules to stick together. And that's a van der Waals interaction. So basically, van der Waals interactions cause atoms and molecules to stick together. Now, these are very weak interactions, but a lot of them at once can be powerful. For example, it's these bonds that help geckos climb up walls. Geckos' feet have tiny hairs to increase their surface area, and all along these hairs, you have van der Waals interactions happening. and that allows them to stick to walls and climb up them. But that's all for today, and if this video helped, please leave a like and hit that subscribe button down below. If you have any questions, feel free to comment them down below and I'll be happy to answer. I can link these notes in the description down below, and I can also link a checklist for review. And good luck studying. Bye.